So this is going to be very different from the other. It's not really class, it's more presentation of things I've done. It's not a general point of view about turbulence. So I hope it works out. I've strung together many things, and hopefully there'll be enough logic and coherence to make it seem somewhat like a class. And for this I have co-workers, Dwight Barclay and Matthew Chantry. And I'm not talking about turbulence in general. I'm going to specify it in two, restricted in two important ways. One is we're talking about wall-bounded shear flows. Not exactly, let's just say shear flows. Where the turbulence is going to come from an imposed shear. Okay, you could produce turbulence in different ways. I like to talk a lot about convection. It's the field I come from, and you can produce turbulence by heating sufficiently or making a sufficient temperature difference. The flow will become turbulent, and other people study that. Or there are things where you push it through a mesh, or different things. But what I'm studying are these flows here, plain Couette flow and pipe flow and Poiseuille flow. Those are the three prototypes. Boundary layer flow can sometimes be put into this category, especially the asymptotic suction boundary layer. I hear that there are many boundary layer specialists among you, so I say things as specific as that. Because in a boundary layer, after all, you have a boundary which is fixed, and then you're sending flow past, so necessarily you have a velocity difference between this velocity and the fixed and the stationary one, so that's shear. Okay. But the ones I'm going to talk about are really these three. In fact, mostly the first one, mostly Couette flow. Couette flow is the flow between two plates moving at different velocities. The view I've shown here is equal and opposite velocities, but you can see by Galilean invariance it doesn't matter if one of them is stationary and the other one is moving. The only thing that matters is the difference in velocities. That's plain Couette flow. Plain Poiseuille flow over on the right is also between two infinite plates, but the flow is produced by a pressure gradient. Okay, the bounding walls do not move. Or they move, perhaps they move if you want to change reference frames, but they do not move at different speeds. And pipe flow is the same thing, but in a pipe with a fixed radius or diameter, like the ones we were hearing so much about yesterday, pi day, and this pressure driven. And all of these flows, okay, we've learned a lot about dynamical systems analysis, and of course, dynamical systems is the way to explain everything. But what did we talk about? We talked about finding fixed points, and then calculating the linear stability, and finding an instability and a bifurcation. And that does not work in these flows, at least not naively, because they are stable. The linear instability for plain Couette flow or pipe flow, there isn't any. That's why I wrote Reynolds number equals infinity. There is one for plain Poiseuille flow, but in fact, it occurs at a much higher Reynolds number than the transition to turbulence. And it's recognized now that these two things really have nothing to do with one another. And yet a lot of attention, you know, a story of the drunk, I guess, who's looking for his keys under the lamp. I know he's bending over, looking at him, says, "What are you doing?" "I'm looking for my keys." And he says, "Oh, you dropped them here?" "No, not here, but you're looking here." "Well, this is where the light is," says the drunk. You know, so everybody's heard this before, I guess, so they don't. Anyway, same thing here. This is not where the turbulence is, but people knew how to do linear stability analysis, and so that's what they did, even though that's not where the turbulence was. There was a lot of literature about this in the 50s and 60s and 70s. But we'll consider that there is no linear instability. So here we have the laminar flow that's linearly stable forever, or equivalent of forever. And somehow the flow becomes turbulent. And so this has been discussed a lot, and one of the advantages of age is that you see fashions come and go, and you get some perspective. So I give you a little tiny historical trip here. In the 1880s, it's like what I said about Faraday or about Taylor. Or these, I mean, people of course saw turbulence since forever, but Reynolds is considered to be the first person to have systematically, scientifically studied turbulence. And he studied the onset of turbulence in a pipe, and this is a picture, a famous picture that's always shown in talks about transition to turbulence. These are 3 pipes, and they have different Reynolds number. Here the Reynolds number basically measures the speed at which you send the fluid into the pipe, the flux, pressure gradient of flux. There's some dye of fluid that's in the center, and you can see for the low Reynolds numbers here, this dye, it doesn't get mixed. The flow is exclusively along the Z direction in this pipe. Okay? And so the dye that's put in the center stays in the center. At intermediate Reynolds numbers, and this is always the problem with this diagram, it's not in the order of Reynolds number, and yet everybody reproduces as it is. Some people have switched it, but this is how it is in Reynolds' 19th century paper. Intermediate Reynolds numbers, there is some kind of meandering. You can see that the flow is not exclusively in the, we call it Z direction for cylindrical geometry, but people often call it X, the pipe. So in this direction, it does meander a little bit, but then eventually that dies out and it's smooth over there. Then for high Reynolds numbers, it meanders a lot, and then that ink fills up the whole pipe. Okay, and so he noted that, and he described, and more or less that's the situation that remained for about 125 years. There's really wasn't an explanation of. A lot of facts were learned, but not. But the solution is really relatively recent. In the 1900s, was developed the famous Orr-Sommerfeld equation, and I can go into that if people want to see it later. Have a kind of class on that. You can reduce Navier-Stokes equations. You write it in an infinite plane. Again, we treat the x and z directions like plane waves, and the direction between the plates is treated, it has to be solved for, and that gives you the Orr-Sommerfeld equation, and that's from the 1900s. And there's a famous theorem of Squires that is very important, and that basically set back fluid mechanics, I'd say, for many, many years, the same way as this result here. I would say set back the understanding. Not that it's not true. So this Squires theorem says that if there is a linear instability in 3 dimensions, meaning you go from something that is just in the x direction with only dependence in the y direction, those are the conventions I'm using, okay? Or I guess you're facing it, x direction, but dependence only in the y direction, then the first linear instability must be something that does not depend on z. This is what's called the span-wise direction in aerodynamics. Okay. And hence that led people, okay, well then we'll look in 2D. We'll look in something that depends on x, the direction of flow, and the y, the direction between the plates. Something that doesn't depend on z. That's a reduction of the problem. And so they did that, and in fact it's in that framework that we have this linear instability at 5772. Squire is right. This is a linear instability that is 2-dimensional, meaning there is no dependence in the span-wise direction. Okay, I feel, this to me in entering the field was a big problem, was to understand these 3 directions. Nothing's round, so everything looks kind of the same. This is, the words are streamwise, that's where the flow is going. Cross-channel between the plates, or let's forget the pipe at the moment, cross-channel, and the other direction is span-wise. It's parallel to the plates, but it's not the direction of flow. So those are the words, and that doesn't change. What does change sometimes is the letters that people use to represent them. I am using X for this, for streamwise, Y for cross-channel, and Z for span-wise. Some people use a different convention where they use Z for cross-channel and Y for span-wise, but I'm not going to do that.
Or the other one.
Or
Z.
you think?
Streamwise, I did it.
Oh, really? Okay. Well, there. Sorry.
That's new.
So, well, in pipes, kind of anything goes, right? That is the Z direction in the in cylindrical geometry, the
Or you can call it
streamwise
X.
one.
You can call it X.
Sorry?
You can call it X.
Call it X, yes. Okay, so, okay, but I'll try to be clear about this, but if you ever have a question of which plane are we looking in, what, you say 2D, but which two dimensions, this always bothers me. People say 2D versus 3D. 3D is clear. We know, in life and space, we have 3 dimensions. When you say 2D, which dimensions do you mean? Right? So what these people meant was this plane, these 2D, this plane that we're seeing right here, that's the 2D. The span-wise direction is coming out at you, and that is the direction in which Squire said you would not see the first linear instability. And if he's right, it's true, and that's the linear instability that Orsac found. The point is, though, that, again, this is like the drunk and the key and the lamp. This is not, turns out to be, not relevant to transition to turbulence. Transition to turbulence is not an example of loss of stability of the laminar flow. Okay, so that's the old stuff. Then more recently, things that I got to live through, in the 1980s, turbulence was seen to be 3D instability of 2D decaying transients. That was a certain school of thought here. Then also in the 1980s was the fashion of strange attractors. Did I hear the word strange attractor in this class, maybe the first or second? Yeah, okay, so strange attractors, I think we mentioned in regard to the Lorentz model. Attractor, meaning that it's the opposite of volume conservation. It's volume contracting. So you go down to an object, you get projected to an object, say a two-dimensional object, but perhaps a complicated two-dimensional object. But the point isn't how the object looks. The point is the trajectories on it move in a chaotic fashion. So the trajectories are not going any old place. They're staying on the attractor, but within the attractor, small differences can lead to divergence. And we saw that in Lorentz model. We saw it going round and round, and then a small difference would make it do this, and then it would do this for a couple of times, which might as well be random. It's not random. It's what's called deterministic chaos. If you really knew to all digits your position, then you would always know the position thereafter. But you don't. You know to a finite precision. You run out of digits of your, each time you go around, you're losing some information you've used up, and eventually two trajectories that differ in the, I don't know, the 15th digit are one is going to go this way and the other's going to go that way. And that's what they say about, that's the problem with weather, is that you can't, if you knew everything to every digit, but you don't and you can't, and you wouldn't have room for it anyway. It's not that there is no actual randomness, it's deterministic, but it might as well be random for all the good that does you. So people looked at turbulence as low-dimensional chaos, strange attractors, but again, I'll say, as I said before, it's not that that's not true. I don't think the work isn't wrong. It just didn't seem to lead anywhere. People no longer talk about strange attractors, or not in those words for that. Then in the 1990s was a fashion called transient growth, and this you've seen. Remember, transient growth is when you have a Jordan block, and let's see, where did we, I didn't emphasize it much, but we'll go back to it here in, here, yes, oh, I'm right at it, here. Okay, here is, right, here is a two-vector, here's two-dimensional dynamical system, so not 2D fluid flow, just two variables. But we have a single eigenvalue, lambda, and say the lambda is negative, so everything should decay. But because it's a Jordan block, and we looked at that again the first day, because it looks like this and not like this, it has repeated eigenvalue, yes, but the solutions are not e to the mu t, they are e to the mu t and t times e to the mu t. So you have initially some growth before decay. And so this was viewed as an exciting, development in transition to turbulence, that you would, yes, you were eventually going to decay if you were linear, but you're not linear. So the idea would be that transient growth would bring you up high, and at that point, you would no longer, linear stability analysis would not apply anymore. The nonlinear terms would kick in, and then you would become turbulent. And again, I feel that none of the actual work, the graphs and equations, so on, are wrong, but possibly the words are wrong, and this does not have any relationship to transition to turbulence. People don't talk about this anymore. So, you know, again, you're used to thinking, well, science is true or false, you progress this and that. The idea that there are fashions and that things aren't wrong, but that just people don't talk about it anymore, that's something that I've had the chance to see over these decades. Okay. In the 1990s was pioneered the idea of turbulence in a minimal unit. This was started by Kim and Walef and Hamilton and Jimenez and Moyne. They tried to see how small a box you could maintain turbulence in. And this is plain Couette flow. And how could you really have turbulence in such a small box? Well, it's periodic. It's periodic, that is to say, the boxes, true boxes, restrict your flow a lot. Of course, you can't have exit flow if you really have a box at the input and output. But in addition, even span-wise, it would restrict you by friction. But if it's periodic, you're much less restricted. So there's a periodic box, but with rigid top and bottom, and it has this aspect ratio. By convention, one takes the height between the plates to be 2 in plain Couette flow, and they found that a box that was 2 by 4 by 6 could maintain turbulence at Reynolds numbers like 400. So it was quite feasible numerically by then. And so that began a big era of numerical calculation of turbulence in small boxes. I'll mention some things that happened around the same time. Walef proposed a self-sustaining process, which I will talk about in more detail in just a moment, and also in about an hour, where you had these 3 objects: streaks, wavy streaks, and streamwise rolls. What are those things? You'll see them in just a moment. And this is an experiment, one of the first experiments in the revival of transition to turbulence in pipe flow in that study. Here's Reynolds number, and they put in different, okay, the idea there was, okay, it's not linearly stable. Linear stability, you will recall, comes from putting in an infinitesimal disturbance and seeing if it grows. Here, they had a dependence on disturbance amplitude. They put in amplitudes of different sizes to see if that would lead to turbulence or not. You know, forget about these infinitesimal ones. And indeed, it does approximately what you might think, which is to say, for lower Reynolds number, you better give it a higher perturbation amplitude in order to go turbulent. And for lower Reynolds number, you need to give it you can give it a lower perturbation amplitude for it to go turbulent. But this diagram was not, it's not very clean, but in addition, when people tried to reproduce it numerically and other things, they found that wasn't experimental error here, that it really is kind of fractal, that you really could not draw a curve like this that said, for this amount of amplitude I will be turbulent and for that amount I won't be. It really was, this boundary could not be well defined. There was this vague tendency, yes, but the fact that you have red points here and blue points there, it's not that this was exactly reproduced exactly as is by further studies, but that tendency was there, and even very careful numerical studies would find that this boundary was, I would say it's complicated, but I would say it's fractal. You really could not draw it because it had, at every scale that you zoomed in, you would find sometimes you would put in some amplitudes and some perturbations, and they wouldn't go turbulent when you would have thought it would, and you would put in some lower ones, and it would go turbulent nonetheless. But this started, there were many studies after this, Mullen and Derbyshire in 1995, along these lines. Forget about the infinitesimal disturbances, let's check out the dependence of the size of the amplitude that leads to turbulence, function of Reynolds number. So that led to a whole school of thought, and as I wrote here, this is called a basin boundary. What's a basin boundary? This you could have learned about, we could have talked about in our dynamical systems classes. When you have two states, which one are you going to go to? We have a very simple example here. We talked about the subcritical pitchfork bifurcation, which we stabilize by adding a fifth order term, so that what we really have is subcritical pitchfork and two saddle nodes. And if we have here, we have what's called bistability. We have two stable steady states. Which one do you go to? Well, if you're here, you'll go here. If you're below here, you'll go there. Hence, we call this unstable branch here the basin boundary. This is the basin of attraction for this state, and this is the basin of attraction for anything that you have. This is in one dimension, so it's very simple. But anything that you have here is going to go here, and any initial condition here is going to go here. So this serves as the basin boundary, and that was what they were kind of trying to do here. But they found that it really could not be decided generally. Then a whole school of thought came in that there were that you could form, that turbulence was visiting, that there were many unstable steady states, which I'm going to talk about it in just a moment, but not probably more after the break. What happened around then is that starting with Nagata in 1988 or 1990, I think it was 1990, he found something that people had not expected, which was that there was not merely this picture that I showed you before, the thing that you see in experiment, which is laminar flow or turbulence. And this is the basin boundary I was talking about, which is drawn deliberately vaguely. That in addition, there existed many other states, but that were unstable. There were many unstable steady states or traveling wave solutions. So that instead of looking like this, I'm talking about pure dynamical systems, or not mysterious turbulence, you had all of these states appearing through saddle nodes, and there were tons of them. People hadn't even found one, and Nagata found one in 1990, and then there was another one found, and then another one, and then came a whole profusion, and by now there must be, 80 or so known. What would you say?
Of that order.
Of that order,
Depends on
yes.
the flow. For each of those flows, probably there's
Many, many more.
20s, tens of.
Yeah, okay, so actually the space looks like that with all of these being unstable. And I remind you that, here I was just drawing a one-dimensional system, but here I'm drawing a projection of something in many, many dimensions. So I don't know, this could be energy or dissipation or something or other. So anything, these are not true intersections. At any given Reynolds number, the space is going to look, if we looked at this in 2 dimensions instead of 1, which at least would be some improvement, we would find that there were steady states all over the place, unstable ones. So I really should draw them as this, the way I'm, right. And this is for fixed Reynolds number, so I'm drawing a slice like that. But it really requires more dimensions, but at least 2 gives you a lot more choice than 1. And the theory was that turbulence is perhaps, this was put forth by Spitanovich and Eckhart, that turbulence was running around visiting these different saddles that was what turbulence was doing at these low Reynolds numbers in shear flow, was visiting unstable points, bouncing off them.